we will continue our work on wind energy, but I thought I would start off by just talking about an issue that I have mentioned in the previous lectures, and I'm showing it on the whiteboard here, and that is what is the significance of the parameter that I've highlighted in red that appears in the definition of the power coefficient, because it's really important in understanding how wind turbines behave to understand where this comes from. The interpretation of it is very simple. Imagine we have wind blowing from the left to the right with a speed of V0, and this blue line that I've drawn on the page here, that is meant to represent a side view of the actuator disc representing a wind turbine. So the area of that blue line is pi r squared. Okay. And what I'm looking at in this diagram here, or what I've meant to represent, is that everything between the red and the blue lines is going to cross the blue line in time delta t. So if the width of that cylinder, it's a circular cylinder, is V0 delta t, then all the air that is within that volume is going to pass the wind turbine disc in that time. And it's going to pass that disc with a, let me change to blue for kinetic energy. It's going to have a kinetic energy per unit mass, which will equal a half V0 squared. The total mass in that volume will be the volume, which will be pi r squared V0 delta t. Okay, area, obviously area times length. Multiply that by the density, and I have the mass of fluid that is in that volume that is going to pass through the actuator disc. And so if I combine the kinetic energy per unit mass with that term, then I get a half rho V0 cubed pi squared delta t is going to be equal to a change in delta t. And I think that is reasonable that if we apply the mathematics correctly and assume continuity and differentiability, et cetera, it's reasonable to come to the conclusion that the time rate change of kinetic energy is given by that quantity there. And you will observe that what I have derived very simply here is the denominator in the expression for the power coefficient. And the very important point that I want to make is that we have a velocity cubed in that relationship. That is really critical to understand. That V cubed comes from the fact that the kinetic energy is proportional to V0 squared, but the amount of mass that crosses the representation of the turbine disc also depends on V0. So the higher the wind speed, the more kinetic energy there is in the wind, but also the more mass of the air that will pass the disc in a certain time. And that's basically where we get the cubic dependence of the power on the wind speed. And the importance of that, if I make a little bit of space over here for myself, is that if we look at the power curve for a wind turbine, then after the cut-in, we have a region where the wind turbine spends most of its time, and I should really call that V0, shouldn't I? That region there, the power output is approximately proportional to V0 squared. And if you go to any wind turbine manufacturer's website, You should be able to download the numerical data for a power curve, or you can get it from the database in SAM, do a bit of power law fitting. And if you do a power law fit for this region of the power curve, roughly 5 to 10 meters per second, you will find that it's an approximately cubic dependence. Okay, so very simple considerations, but considerations that give you a lot of information about how wind turbines behave in terms of the form of the power curve for that range of wind speeds. And of course, then that fits into combining that with the probability distribution of the wind speed to get the annual energy production. Okay, so I'm going to stop sharing that screen, and I'll pull up my lecture 5. And whoops, I will need to start sharing again if I can find what's happened to, yep, here we go. So share screen again. And I move on to lecture 5. Okay, so this is the same front page that I had for the previous lecture, which we finished last week. What I want to talk about today is mainly about turbine siting, safety and noise. And I'll talk a little bit in terms of turbine siting. I'll talk a little bit about some of the other issues about public acceptability and danger and damage that wind turbines cause as well. Before I do that, I just point out a very simple calculation, again, similar to what I did on the whiteboard, that is meant to give you a sense or an understanding of why the twist angle of a wind turbine blade changes as you go along the blade. And the example that I have is a turbine is operating at its maximum efficiency. So according to the Betz-Joukowski criteria, the axial induction factor will have a value of about 1/3. If we take a tip speed ratio of 7 as sort of a representative value for modern large wind turbines, the question is, estimate the pitch angle necessary to achieve an angle of attack of 6 degrees at a radius of 1/4, 0.25 of the tip radius, and then at the tip radius itself. The motivation for this value of the angle here is that for a wide range of airfoils, the maximum lift to drag ratio occurs at an angle of attack of around 6 degrees. It changes from airfoil to airfoil, but it doesn't change very much. So even if this blade has different airfoils out along the blade, this value will be roughly constant. And it's basically just a explanatory exercise anyway. So if we look back at the blade element diagrams that we looked at in the last lecture, if the axial induction is 1/3, the velocity at the blade is 2/3. And at the quarter radius position, the local circumferential velocity normalized by the wind speed will be 1.75. And the inflow angle, which is defined in those velocity diagrams, is given very simply by this expression here. And that gives an inflow angle of nearly 21 degrees. And so the pitch angle has to be that angle minus the ideal angle of attack of about 15 degrees. If we go out to the tip and redo the calculations, so that symbol should be lambda. Somehow the scientific notation got changed back to text notation. That should be lambda, just like lambda in this equation here. And there we get an inflow angle of 5.44 degrees, and that gives us a pitch angle of minus 0.56 degrees. In fact, many large wind turbines have negative pitch out near the tip. And the single reason why we get that substantial variation in the pitch by about 15 degrees is simply that the circumferential component of the velocity has changed substantially. it's changed by a factor of 4. And that, combined with the tip speed ratios being very high, means that the pitch angle has to change. Okay. Again, a very simple demonstration. It's no more than a demonstration, but it does give you a sense of why the turbine pitch angle has to change. The final thing that I would like to make about this example is that it is assumed that the axial velocity is the same at both positions. So U1 over U0 is the same value here as it is here. That's, again, for explanatory purposes, that's a pretty good approximation. If you look at the flow coming into a wind turbine, particularly around about the conditions of maximum efficiency, then the axial velocity going into the wind turbine will be approximately constant. So this is a useful example to demonstrate the importance of pitch angle changes, largely to keep the angle of attack as close to the optimum value from as much of the blade as it can. Okay, does anybody have any questions on what I've done there? Like I said, both the things that I've done today are pretty simple examples. Okay, so if I ask for the next one. So we're going to look at some of the issues about sighting, a little bit about safety. And if you have some spare time, I suggest that you go to YouTube and on YouTube search for turbine failures. And there's some really good videos there. This one here is one of my favorites. Unfortunately, it's a fairly old video, and the frame rate is quite low, because this video shows a turbine rotating and a blade disintegrating. And unfortunately, the blade disintegrates between one frame and the next. On one frame, you see the 3 blades, and then one frame further on, you only see 2 blades. That unbalances the turbine. One of the blades crashes into the tower and the turbine collapses. So it is pretty exciting. And you can see a lot of other types of turbine failures as well, including, I think I've got on the next slide, including ones associated with ice. And here's an example of ice throw from a wind turbine blade. And here's an interesting example of some of the other problems that happen with icing. Often wind farm owners will shut down their turbines if there's going to be a large icing event. So if they are confident that there's going to be large accumulation of ice on the blades and the tower, they will shut down the turbine and wait for the icing event to finish. The problem with that, of course, is that can leave a large amount of accumulated ice on the turbine. And this is one way that you get rid of, not a very effective way or not a very environmentally friendly way, as this caption says. But a lot of modern wind turbines now have heating in the blades. There's various devices to allow the surface of the blade to be heated, which can both prevent ice from forming in the first place, or if it does form, that you can get rid of it. There's quite a number of specific issues that come up when turbines are operating in cold climates, like we get in Canada and like you get in Russia. And there's been a large amount of research and development work going into things like how to prevent icing on the blades, how to make sure that the various materials of the blades withstand the cold climate, et cetera, et cetera. Unfortunately, we don't have time. I'm not going to talk any more about that. Okay. Here's your homework exercise for this week, or for tonight, my time, Wednesday morning, your time. We'll talk about it again tomorrow. This is a relatively small turbine. This is only a 10 kilowatt turbine that failed in the United Kingdom in January 2013. I happened to be in England at the time, and I saw these photographs in a newspaper. So I went to the newspaper website and I downloaded all the photos that I could find of this turbine. And I tried to reconstruct the sequence of events that caused that blade failure. The only thing that we know for certain was that there was a very big storm that day. So lots of wind, lots of rain, and this turbine, along with a number of other turbines, failed. And you can see a couple of pictures of the turbine. Here it is with two failed blades. Here's two failed blades here. And it looks like you can just see at the top, probably the blade up there has been detached. Here it is partially under reconstruction. But I'd like you, if you have some time, and here is the turbine lowered to the ground in order to take the three damaged blades off the turbine. I'd like you to think about what might be the cause of that blade failure. And tomorrow, before we start, I will I'll go through my reconstruction of the event. Okay, there's, again, a whole pile of really good images available on turbine failures. A lot of them involve generator fires. And most of the ones here, when you get a lot of smoke and flames, you can bet that the generator's involved. So obviously, like any other energy generating technology, there are dangers associated with wind turbines. Blade failure is a major danger because a blade is heavy and can damage people and equipment. Ice throw from a turbine, I forgot to mention it before, this is a piece of ice that actually detached itself from a wind turbine blade and was thrown a large distance away from the turbine. So they're all potential hazards. Some of the effects of wind turbines are not actually life-threatening. Noise can be an issue, and I'm going to talk about that in a moment. But before we get on to noise, let's see if I can play this video. This is a video about shadow flicker. Here we go. It's only a short video. I won't say anything till the end. There we go. Sorry, it's restarting. Okay, so this is a house near a wind turbine. So we're inside the house. Okay, so that's an example of what's called shadow flicker. What's written at the top of the screen there. If you get the right conditions of the position of the sun and enough wind for the turbine to be generating power, then you can sit in your house and see the shadow of the blades pass your walls regularly. And I don't think I would like that. And I suspect quite a few of the people listening wouldn't like it at all. So these are some of the issues associated with the acceptability or the social acceptability of wind energy, which is a very important issue. One of the reasons why the offshore wind industry has developed is that if you move the turbines offshore, then you reduce the opportunity for problems like shadow flicker and noise to upset people. Okay, so if I can move forward. Okay, noise is an extremely important issue with wind turbines, and it has a lot to do with their public acceptance. For some reason, I think it's because a lot of the objections, the original objections to wind turbines were because of noise, that wind turbine noise, I think, has become an issue that's much more talked about than is important. There can be issues, there can be problems with noise. I know of a few examples where noise has been particularly important. And in the early turbines, particularly turbines where the blades were downwind of the tower, those turbines could produce tonal noise. In other words, noise at a reasonably constant frequency, even as the wind speed changed. And tonal noise is much worse noise to deal with than noise that doesn't have any tone. If you look at the numbers here, 1,000 feet, this is obviously an American document, 1,000 feet is about 300 meters. So that would be the typical distance between a turbine closest to the boundary of a wind farm and the boundary of the wind farm. So we're already looking at noise levels that are not very large. And that is generally the case with wind turbines, that their noise output is not great, but it's something that everybody is very sensitive about because it factors into whether communities will accept a wind farm in their area and things like that. It's a very, very simple example of noise calculations for a wind turbine. Noise assessment or noise computation is an incredibly complex task. If you're going to do it properly, it requires time-resolved, three-dimensional computational fluid dynamic simulation of the flow over the turbine. It's extremely complex. Most of the noise on a turbine, and that's what this old image is meant to show, is aerodynamic noise. In other words, noise that is caused by moving through the atmosphere. And if you look at the aerodynamic noise of a wind turbine, there's about 6 different causes. There's 6 different sources of noise on a wind turbine blade. And getting all that right is a difficult thing to do. And often what happens when you're dealing with a very complex problem, people resort to very simplistic models for what's happening. And what you see up the top here is a very simple correlation for the sound power level of a turbine, depending on the circumferential speed of the tip and the radius of the turbine. And so if we do the calculations for a Vestas V80, which is an 80-meter diameter turbine rated at 2 megawatts, then we get a sound power level of about 107 decibels, significantly greater than the example here, because this, I think, is a 500 kilowatt turbine example. It's quite an old one. However, that's not the noise level that people see. This is what's called the sound power level, which gives a measure of the strength of the source of noise. To compute the noise that's received by an observer, we have to use an equation that translates the sound power level into a noise level at some distance from the observer. So whenever you see a noise level in decibels, then it must always be accompanied with a statement of how far away from the source you are. Because obviously, the further you go from the source of noise, the lower the noise is going to be. So this very simple hemispherical spreading equation says that the noise level heard by an observer and the subscript A is there to represent that this is an A-weighted decibel scale. In other words, the noise is factored by the frequency response of the human ear. So, for example, the human ear, even for you young people, can't hear below about 20 hertz. And so that region of the noise in Fourier space is filtered out of the A-weighted scale. So we have a sound power level, and then we have what's called a hemispherical spreading model. And noise levels are always given in decibels, which is a logarithmic scale. That's what the logarithmic factor is showing here. And basically this term here says that if you think of a wind turbine as a point source and you go away from that source at ground level by a distance that is large compared to the tower height h, then the noise is going to spread hemispherically. So this assumes flat ground and hemispherical spreading, which is often not the case, but this is a good enough approximation, at least to give a basic idea of what is happening. And then you have to factor in that noise is actually absorbed by the atmosphere. Okay, this is because the molecules of air in the air are actually discrete and they can actually absorb in their internal motion some of the energy that sound represents. And then this factor here is simply a scaling factor governed by the noise criteria. Now, governed by the definition of the decibel scale. You plug all those numbers in, and if you say, I want to go 500 metres away from a turbine with a 80-metre tower, I'm going to hear a noise output of about 48 decibels. And to put that into context, here's another noise scale here. You can find many of these scales on the internet. 48 decibels is somewhere between a bedroom and a quiet office. Okay, it is not particularly noisy. Of course, if you have more than one wind farm, which you do in if you have more than one wind turbine, which you do in a wind farm, then the noise is going to compound, and that will increase it. But turbines tend to be several hundreds of meters apart anyway, so you're probably not going to get distances less than about 500 meters. And the other thing that I want to say about wind turbine noise is that what you actually hear is the turbine noise above the background noise. And the background noise can be a whole range of things. It can be cars moving on the freeway next to the wind farm. It can be the wind noise in trees if there are trees on the site. It can be due to rain. There's a whole range of causes of background noise, and those causes are variable. So the background noise at one day can be quite different to the noise at another day. And that's one of the problems with assessing wind turbine noise, because the turbine noise is often not much larger than the background noise. And what I'm trying to represent here in this diagram here is a particular feature of wind turbines, that it's often the case that the noise from a wind turbine changes less with wind speed than the background noise. Okay, I've done quite a bit of work over the years on wind turbine noise at different sites, and every time I see the data from a particular site, I see this result here, that the turbine noise relative to the background noise gets less as the turbine noise increases. Obviously, what's happening is that it's a function of wind speed. As the wind speed increases, normally the turbine power increases, therefore its noise increases, but the background noise level increases. So wind turbines tend to be their most noisiest down around about 4 or 5 meters per second wind speed. And the magnitude of the noise, even relative to the background, is even less than what is shown in this diagram here. So generally speaking, my take on wind turbines and noise is that noise is generally not a problem. There have been situations. A number of years ago, there was a wind farm in the Netherlands installed at a site that had unexpectedly high winds at nighttime. And so all the nighttime calculations of the noise output of the wind farm that were made before the approval for the wind farm was done, they turned out to be wrong. And there was a big campaign by the people in the area to get the wind turbines turned off at night because of that. Okay, one of the other features of wind turbines that's extremely important from their siting perspective is something that I haven't really said anything about so far in this course, and that is the fact that wind speed changes with height. Okay, if you know anything about meteorology, you'll know what I mean when I say the atmospheric boundary layer. The first several hundred meters above the Earth's surface is in effect a boundary layer flow. The wind speed at the ground is zero, and normally it increases with height. And one of the issues with wind resource assessment is that we need wind speed data at high heights. You know, nowadays, an 8 megawatt wind turbine will have a hub height of 140 meters. To get wind speed information at those sorts of heights is a difficult thing to do. So one of the things that can be done, and this is what is done in SAM, if you pay attention to the wind module in SAM, is that when SAM asks you for a wind speed, it asks you for a wind speed at a particular height, and then it extrapolates that wind speed to the hub height of the wind turbine before it combines the Weibull distribution with the power curve to get the annual energy production. And there's basically two ways that extrapolation is done, either through what's called a power law. And the power law says that the wind speed varies with height, which is the symbol Z. HR is a reference height. And the power law is a function of the terrain type. In other words, if we have relatively smooth surface like calm open sea, the value of M is relatively small. When we move to much rougher conditions and about the worst on the planet, the centers of cities, then the roughness, the factor M is much greater. There's an alternative called the log law, which is actually theoretically more justified than the power law, because the log law can actually be derived from the time average Navier-Stokes equations that describe neutrally buoyant flow. But it's slightly more complicated to use, and it involves what's called the roughness length, stated here. And you can see that the roughness length, as you probably would expect, increases as we go from a smooth surface to a very rough surface. So often what is done is, if we don't have measurements at the hub height of the turbine, then if we have measurements at lower heights, then we can extrapolate that. Okay, the problem with those laws, and they're not really laws. I mean, they have nothing like the status of Newton's law. They require flat terrain, constant roughness, and neutrally buoyant flow. And you don't get that very often with wind farms. Often wind farms are sited on hilly locations, and the roughness around the turbine can change, and that can influence the way in which the wind speed varies with height. So what that means for wind turbines, and particularly at the stage when you do wind resource assessment, is that you need to get information that is as close as possible to being representative for the hub height of the wind turbine. And usually what happens in the development of a wind farm project is that the first stage of the project will be the prospecting for wind energy. Just like we prospect for gold or prospect for oil or other resources, we prospect for the wind resource. And that is normally done with a anemometer mast. And here's an anemometer mast. It's actually in North Calgary. It's owned by a local wind resource company, and that company has given us access to the data from that mast. And we've done quite a bit of analysis for that data. And on this anemometer mast, at every 10 meters, there is at least 2 anemometers and the wind vane. And the anemometers measure the wind speed in meters per second, and the wind vane measures the direction, because wind direction is really important, particularly in terms of interference of one turbine by another. So if I'm involved in a wind farm project, the first part of that project would be to put up an anemometer mast and maybe 3 anemometer masts on a potential site and measure the wind regime for about a year. And that's really absolutely necessary as part of the wind resource assessment process. That information, I wonder if this video will work. Yep, it's working. Here's a wind mast, an anemometer mast. Okay, you can see a wind vane coming off the mast. You can see the turbines in the background. So that mast would be at the hub height of the turbines. And did you notice at the end of the video, let me see if I can get that back again. I'll have to go to previous. Okay. Notice here on this still, there's 2 anemometers, one here and one here. Now, these are the anemometers at the top of the mast. And so they would be at the hub height of the wind turbine. Does anybody know why they use 2 anemometers? It's an interesting question. These are very simple cup anemometers. You can probably imagine 3 cups that are on arms that are spun around by the wind. And the angular velocity of the cups is calibrated in a wind tunnel against the wind speed. And then it's put on an anemometer mast. Now, an anemometer mast, if it's 80 meters high and you want to rent an anemometer mast for a wind farm project, that will cost you about $50,000 a year. Okay, they're very expensive. An anemometer, one of these anemometers costs about $1,000. So the actual measuring equipment is a very small fraction of the total cost of the mast. And so duplicating the anemometer is cheap. And that gives extra confidence that you're getting good results. And particularly in a climate like Canada and Russia, the biggest problem that you have with these cup anemometers is icing on the anemometer in wintertime. If there's enough icing that occurs, the anemometer will actually seize. It won't be able to turn. And so if you have two anemometers, then what they look at when they're processing the data is any situation where there's a significant difference between the wind speeds indicated by the two anemometers. And if there is, that's possibly an indication that one of them is affected by icing. I don't know what the situation is in Russia, but in Alberta, every wind farm has to have an anemometer mast. And in addition to that having that anemometer mast, the wind farm owner must send the data from that wind mast to the Electricity Authority of Alberta. There's something like 25 wind farms in Alberta. So that's a huge source of data. And one of my research activities at the University of Calgary is using that data to look for the correlations between different wind farms in terms of power output and things like that. And I'll talk what the significance of that later on in the course. So a wind mast is essential for the assessment of a wind farm. And when the wind farm is built, one of the anemometer masts usually stays in place as a statutory requirement for actually operating a wind farm in Alberta. Okay, what happens then is that wind data is processed. And it's processed by some pretty sophisticated software. Here is an example of the manufacturer's or the software provider's specification of a very well-known piece of software called WindFarmer. And WindFarmer is made available by DNVGL, which is a big consulting company in Europe. And what it does is take the data that comes from the wind mast, do all the things that you see here, and optimizes the wind farm layout. And what that means is that computationally, it models the wind flow over the wind farm site, and it moves the wind turbines around until you get the best possible outcome, usually in terms of optimizing the annual energy production. But of course, there are other constraints on that as well, like the further the wind turbines are apart, the higher the electricity connection costs, and those sorts of things have to be explored. Now, this is not meant to be an advertisement for this particular piece of software. What it is meant to be is an indication of the detailed engineering and analysis that goes into actually developing a wind farm site. One of the reasons for that is shown in this photo here. And you may well have seen this photo before because it's one of the most famous photographs of wind turbines. It's one of the early offshore wind farms off Denmark, and the wake of the wind turbines has been visualized by water vapor condensing in the low pressure area behind the blades. And you can see, so for example, you can see the wake of the front turbine. But the interesting thing here is that the wind direction is such that the wind flow over the front turbine is flowing over all the remaining turbines. And if you think about the consequences of that, it is severe because a wind turbine's job is to extract kinetic energy from the wind. And so if these front turbines are extracting as much kinetic energy as they can, that leaves less kinetic energy for the ones behind them. And as you see from this figure here, that can result in a very significant reduction in power. This sort of effect is almost impossible to prevent when you're laying out the wind turbines on a wind farm, but what you can do is minimize it. And it also shows you the importance of knowing the wind direction, okay, because these interference effects are primarily caused by the wind direction aligning with directions of rows of the turbines. So later, offshore wind farms don't use a layout rather like this, or alternatively, one would hope that the wind blowing in the direction that it is a very rare occurrence for this particular wind farm. Like I said, it's impossible to prevent this from happening. You just want to design or lay out your wind farm so that you minimize the effect of one turbine interfering with another. Okay, just a few more things about wind turbine safety, and the safety of the blades is probably the most critical issue with wind turbine safety. And what you see here are what are called static tests of the blades. So a wind turbine blade is a complex cantilevered composite shell structure, and it has very anisotropic properties, because when a wind turbine blade is made, most of the fiberglass reinforcement goes to give you strength in the radial direction so that you withstand the bending of the blade due to the pressures of the wind. When blades are made, blades of all sizes go through a static test. And this static test, where you simply pull the blade away from its mounting, you can see at the back here, or more clearly here for this smaller blade, that gives you measurements of the deflection of the blade. And that is very useful information from the structural perspective, because you can compare those measurements to the prediction of usually a finite element structural model for the blade. And that's a really important part of ensuring that a wind turbine blade is safe. Wind turbine blades are also fatigue tested. And here's a small wind turbine blade being fatigue tested. Here's a large blade being fatigue tested. And usually when large blades are tested, it's only the inner part of the blade that is tested, because it's more difficult when you've got very long blades to arrange for a fatigue test of the whole blade. And basically what happens is that the blade is shaken up and down. Known loads at known frequencies. The loads and the frequencies can be varied, although they tend not to be for large turbines, to mimic the forces that the turbine blade will see in a 20-year lifetime of the blade. And again, this is really critical for the structural integrity of the blades, and the international standards from the International Electrotechnical Commission that govern wind turbine safety, they make it a requirement that each new blade design is fatigue tested. And finally, that's just showing you what can happen with a finite element analysis of a wind turbine blade. In this case, a small blade, but analysis is done on blades of all sizes. This is I forgot to put the scale on this figure, but this figure shows the strain on the blade, the deformation of the blade surface due to the loads that are going on it. And this is quite a complex process, because even on a small wind turbine blade like this, there could be a large number of layers of reinforcement. And most of those reinforcing layers are in the radial direction, but there are also reinforcement in the plus or minus 45 degrees. And the reason for that is that we don't want a wind turbine blade to twist. If a wind turbine blade twists during operation, that changes the pitch angle of the blade. And if you change the pitch angle of the blade, you change the aerodynamics of the blade. And even very small pitch angles, even pitch angle differences of around 1 or 2 degrees, can have a major influence on the aerodynamic performance of a wind turbine blade. And so blades are often designed to be relatively soft in bending, but nearly always extremely strong in torsion. And that's relatively easy to do with a basic airfoil shape. And I think Yep, that's it for that lecture there. And I'm pretty sure that finishes the sections on wind energy. So what will happen tomorrow is the start of the last energy generating technology, photovoltaics, and we'll have probably tomorrow and most of next week on photovoltaics, and then we'll move on to issues of energy storage and system integration. So I think it's probably best if we don't start on photovoltaics now, because I would need to probably repeat the information tomorrow anyway. So I'll ask if anybody has any questions on what we've talked about today, or indeed on anything that we've talked about so far in the course.
I have a question about noise.
Mm-hmm.
We have some kind of myth in Russia that you didn't say anything about frequency response of this noise, and we have some kind of myth in Russia that infra noise have a significant impact to environment, so it could be unfriendly. Maybe you could comment it. I mean, what we do we know something about frequency below than 20 hertz?
Yes. So infrasound, as it's sometimes called, is the noise that occurs below the human threshold for hearing, which is roughly 20 degrees if you're young, probably higher when you're older. So you don't hear it, but it can have physiological effects on a human body. And there are people who argue that infrasound is actually, or susceptibility to infrasound is sort of like an illness. And relatively speaking, a wind turbine does not produce a large amount of infrasound compared to the sound levels in the range of frequencies that people can hear. But it has been an issue that opponents and proponents of wind turbines have argued about. It's one of those areas that's extremely difficult to come to a rational conclusion about, because any measure of the effects of it are sort of down around the noise level, noise in the sense of variability of the results that you can do the study. I think a similar thing happens with the idea that people's health is affected by whether they live near power lines. You know, the electromagnetic field of a power line is supposedly can cause some people to get sick. Now, all the statistics that you see on that, again, you know, the occurrence of the illnesses is so low that they're down around the noise level of the observations anyway. So I don't dismiss the fact that it can be important. What I do say is that from what I've learned about it and read about it and talked to people about, it's not something that can be objectively demonstrated. And that's a difficulty. One of the interesting things about infrasound, one of the most common sources of infrasound is surf on a beach. You know, that when waves break on a beach, apparently they generate a relatively large amount of infrasound. I've never heard anyone complain about that.
Yeah.
No, and I think the reason is that you go to the seaside for a holiday. You know, a lot of issues about noise for wind turbines, I think, are often a roundabout way of complaining about the turbines, you know, because you can't, someone who is protesting against a wind farm development in their community, you know, they're not allowed to get up and say that they oppose renewable energy. because socially that's not a good thing to do. So what you do is you stand up at a public meeting, and I've seen this. I can tell you some good stories about this. They get up at a public meeting and they say, I'm all in favour of wind turbines, but the noise level for our community is going to be too high and we can't have them here. And that's a cynical view of those sorts of things. So, but it is potentially an important issue. I mean, we saw what happened with shadow flicker. I mean, I would hate to live in that house and see that level of shadow flicker. You can't say that it's not real, but what you can say is that it's extremely difficult to objectively determine what the problem is and make your criteria based on an objective level.
Thanks.
Okay. Sorry.
Also one question about is it right that each turbine have own anemometer, right? For control purpose?
Yes.
The purpose of this anemometer is just
Yeah. That's true. I'm actually going to talk about that in the next lecture.
Okay.
I got confused. The reason I got confused is that I'm currently teaching a course in Calgary that's somewhat similar to this course, but has different. But yeah, the next lecture I'll talk about generators and control, and that's a really interesting aspect of wind turbines because, and this is something that people might like to review before the class tomorrow. We know that a wind turbine produces its maximum power when it operates at a constant tip speed ratio. Yeah. The tip speed ratio involves the wind speed. So what that means is if you want to keep the power output at a maximum as the wind speed varies, then the generator speed has to vary with the wind speed. And you have to design a control system that does that without actually measuring the wind speed. So it's quite a challenge, and I'll be telling you about that tomorrow. Sorry, I'd forgotten that we're actually moving on to photovoltaics next week.
Yes.
Okay. It's now 8:30 my time, 9:30 Wednesday morning your time. So we shall finish for the day unless there's any final questions or comments. Okay. Doesn't look like it anyway. As I said, please feel free to email me if there's anything you want further information on, or use the chat if you would like to do that. Okay, see everybody tomorrow.